So we've spent the last few times talking about polynomials divided by other things. So let's consider today a polynomial function, 3x to the fourth minus 8x squared plus 9x plus 2. And for no other reason than, why not? Let's take f of x and try dividing it by a polynomial x minus 2. So we know now that by synthetic division, we can go 3, and then since there's no x cubed term, we put down a 0, negative 8, 9, and then 2. We put in the box, since it's x minus 2, we take that 2 and put it here. And the way it goes is 3 comes down, then 3 times 2 is 6, add them together is 6, 6 times 2 is 12, add them together is 4, 4 times 2 is 8, add them together is 17, 17 times 2 is 34, add them together is 36. So these four numbers form the coefficients of the quotient, and then in order, that's constant x, x squared, x cubed, so we can write down 3x cubed plus 6x squared plus 4x plus 17, and then this tells us the remainder, so we write plus 36 over x minus 2. And sort of in general, we know that if f of x is a polynomial, then we can do the following, where we take f of x and then divide by x minus k, and that's going to produce for us a quotient, which is a polynomial. So in this case, the quotient goes from there to the 17, plus some remainder over x minus k. And this is something that we can do in general because we have an algorithm to do this. Now, sort of bear with me. I'm just going to try something. And I'm going to say, what if I take this denominator x minus k, and then I multiply both sides by x minus k? So then I would end up over here with f of x, and then on the other side I would have x minus k times q of x plus, and then multiplying both sides would get rid of the denominator, so I get plus r. Okay? Now, from here, I want to take this r and focus really closely on that, because that r represents the remainder, evidently. Now, what if I made the claim that I could plug k in for the x? So this number k, I'm going to try to plug it in for the x. And I would claim that f of k is equal to, well, k minus k is going to be 0. So this whole thing is going to be 0 times anything is 0 plus r. And so then f of k would equal r. Okay, well, let's try that over here. So k right here is going to be 2. So I'm going to say, what if I take the number 2 and plug it into f of x? So that would become 3 times 2 to the 4th power minus 8 times 2 squared plus 9 times 2 plus 2, which is going to come out to 3 times, that's 16, so that's 48, minus, that's 8 times 2 is 32, and then plus 18 plus 2. So this gives me 16 plus 18 is 34, plus 2 is indeed 36. Okay? So the claim was, if I take the number k, so that k, that k, that k, and plug it into f, which I did, then the result I get is the same thing as the remainder. Okay? And this isn't a coincidence, because I showed here that there's some kind of logic behind it. Now, you might object by saying, at this stage, I thought x could not equal k, right? Because x minus k is in the denominator. No one would say, oh, well, x cannot equal k. And then after doing that, I went and plugged k in for x, which I shouldn't be able to do. Now, you have a very good objection if you're saying that. So it turns out this can turn into that everywhere except x equals k, naturally, without any kind of complications. But it also turns out, if you're very careful with how you define things, and you'll learn about this later in calculus, that you can still establish a connection between that and safely say that this is always possible, even when x equals k, by using suitable limits. We won't go over that here. I just want you to take on faith, unfortunately, that this to this is a valid connection, and you can write this down even when x equals k. So as a result, we have this sort of fascinating idea that f of k is equal to r. And so this is what we call the polynomial remainder theorem. And that says the following. So if f of x is a polynomial, then the deal is, if I take f of x and divide by x minus k, where k is some number, then this has a remainder r, which is equal to f of k. So if I take this number k and I plug it into what f of x is, then that will arrive at the same result as my remainder when I perform the division. What it's saying is, if I do f of 2, the number I get, that 36, is the same thing as the remainder when I divide by x minus 2. So this number should match that number. That's what the polynomial remainder theorem says. Now let's try it one or two more times to lock it in. So this time, let's take our same f of x and let's try dividing by x plus 1. Okay. And so by synthetic division, we're going to write down the coefficients again: 3, 0, negative 8, 9, and 2. And then in the box, since it's x plus 1, that's the same thing as x minus negative 1. That number is going to go in the box right here. So 3 comes straight down, then 3 times negative 1 is negative 3, add them is negative 3, times negative 1 is 3, add them is negative 5, times negative 1 is 5, add is 14, multiply by negative 1 is negative 14, and then add them together gives me negative 12 at the end. So what that's supposed to do is, I get a quotient 3x cubed minus 3x squared minus 5x plus 14 with a negative 12 remainder, like that. Okay. So what we're trying to check is, by the polynomial remainder theorem, that what I've done is I've gotten a remainder, and I'm going to see if that remainder matches f of negative 1. So let's try this. F of negative 1 equals, so I'm going to plug that into up here. So this is going to be 3 times negative 1 to the 4th minus 8 times negative 1 squared plus 9 times negative 1 plus 2. So negative 1 to the 4th is 1, so it's going to be 3. And then negative 1 squared is 1, so that's going to be times negative 8. And then minus 9, and then plus 2. So this put together is 3 minus 8 is negative 5. Then that gives me negative 14, plus 2 is negative 12. So we have a match. This number matches this number. So far, polynomial remainder theorem, pretty good. Let's do one more. Okay, this time, let's try the same f of x, but we're going to divide this by x plus 2 this time. And so, we're going to set up synthetic division: 3, 0, negative 8, 9, and then 2. And in the box, since this is x minus negative 2, we're going to put negative 2 in the box. So the 3 comes right down. 3 times negative 2, negative 6. Add them together, negative 6. Multiply them is going to be 12. Add them together is 4. Then this is going to be negative 8. Add them together is 1. 1 times negative 2 is negative 2. And in the box, I have 0. So apparently the remainder is going to be 0. Well, if I write this out, then I would say that's 3x cubed minus 6x squared plus 4x plus 1. And there's no remainder, so I don't have to write anything. Interesting. Okay, well, let's check the polynomial remainder theorem. Let's say if I do f of negative 2. So then that means I'm plugging in negative 2 into there. So that's 3 times negative 2 to the 4th minus 8 times negative 2 squared plus 9 times negative 2 plus 2. So negative 2 to the 4th is positive 16 times 3 is 48. Then negative 2 squared is 4 times negative 8. And then minus 18 and then plus 2. So this is going to become positive 16. Subtract that gives me negative 2. Plus 2 is 0. So this number matches that number. Now, of course, at this stage, you should be looking at this and thinking, okay, fine, that's nice. We have some consistency. But how could this possibly be useful? And that's where this example comes into play. So in this specific instance, we managed to get a remainder of 0, which matches the fact that f of negative 2 is equal to 0. So perhaps you would recognize this as maybe an x-intercept corresponding to the point negative 2 comma 0. Because when x is 2, y is 0. Okay? This is what we're going to call a 0. So I would say the 0 of f of x is currently x equals -2. And maybe there are others, but I've definitely found one. By definition, a 0 is the value of x that will make f of x equal to 0. Okay? And additionally, if I look back here, I don't have a remainder. So if I were to take the same kind of procedure I did over here and take this x plus 2 and multiply it over, I might get something very interesting. Let's see that next. So let's multiply this x plus 2 to both sides. That will get us f of x equals x plus 2 times 3x cubed minus 6x squared plus 4x plus 1. Now, if you take this and expand this out, guarantee it will be the same thing as that original polynomial, hence f of x equals. But what we have here is a factored version of the original by doing this process. So this gives rise to the factor theorem, which says a polynomial f of x has a factor x minus k if and only if, which we write with two f's, if and only if f of k equals 0. So what this is saying is, if we perform this division, then we would get a remainder, which is equal to f of k. But if f of k equals 0, which means the remainder is 0, then we're able to take f of x and write it as x minus k times q of x, where q is the quotient that resulted from the division. X minus k is that factor we divided by, which now shows up over here as a factor, and there's nothing else because the remainder is 0. And this is sort of a powerful thing, because really what that means for us is going forward, we can start trying to factor polynomials by using synthetic division and getting a remainder of 0. Getting a remainder of 0 will tell us a factor of f of x, and it will also tell us that f of k is equal to 0. Keep in mind that factors and zeros have been connected for a very long time in our math history. So let's take this that we just discussed and apply it to something that is familiar to us. So let's consider an f of x that's equal x squared minus 4x minus 12. Now, we already know how to factor that quadratic. We know that numbers that add up to this and multiply to that are -6 and +2. So we know the factorization is going to be x minus 6 times x plus 2. But let's just pretend we don't know that. So let's just say if I take f of x, and I don't know, I'll divide it by x minus 6. Well, by synthetic division, I can write 1, -4, and -12, and then put 6 in the box. So then 1 comes down, 1 times 6 is 6, add those is 2, 2 times 6 is 12, and I get a remainder of 0 with a quotient of, that's constant in x, so this is going to become x plus 2. Now using this, because I have no remainder, right? Because I have no remainder, I know that f of 6 is equal to 0. And I can confirm that, right? If I take f of 6, then that's going to be 6 squared minus 4 times 6 minus 12. Now this is going to be 36 minus 24 minus 12, which is 0. This 0 matches that 0. Okay, so far we're good. And then we can say, using that, we know that f of 6 equals 0, so we can argue that x minus 6 is a factor of f of x. Really what that means is if I take this and multiply it to the other side, I'm able to rewrite f of x as x minus 6 times x plus 2. Now, none of this is novel to us. We knew that we could do this from the start. What we're trying to do here is take something familiar and make sure it fits with this set of formalisms. Now, at the end, right, what we used to do is say, well, this factorization really tells us useful stuff in this context. Because what we can say is, what if we want to take this and set it equal to 0? So if we are really interested in f of x equals 0, for example, we want to find the x-intercepts, we would say 0 equals x minus 6 times x plus 2, which would then say x is equal to 6 or negative 2. And these are the zeros corresponding to these factors. What we want to do now going forward is figure out how to factor things that are more complicated. Let's do one more. So consider an f of x that is x cubed plus 64. And let's just say the goal is to factor that thing. So what we want to do is divide by an x minus k, where we get a remainder of 0, which tells us that f of k equals 0. So we have this, and then we conclude that x minus k is a factor, right? So I want to do a division process. So let's start the synthetic division, 1, 0, 0, 64. And in this box, that's where k goes, but I don't know what to use for k. So I'm just going to guess something and see where it takes me. So if I guess 3, 1 comes down, 1 times 3 is 3, add together is 3, 3 times 3 is 9, add together is 9, 9 times 3 is 27, which adds up to 91. And that is not 0. So this is 91, which means that's 91, which means we fail at this point. So evidently x minus 3 is not a factor. So we have to guess again. Now this time, let's try a number like negative 4. So 1 times negative 4, add them together. Negative 4 times negative 4, 16. Add them together is 16. 16 times negative 4 is negative 64. And oh look, I get a remainder of 0. So my remainder is 0. F of negative 4 is 0. So here's the deal, right? F of negative 4 is equal to 0, which means from here, I can say that x minus negative 4 is a factor. So I can say x plus 4 is a factor. Now, if I were to write this as f of x divided by x plus 4, right, we could write this as the quotient here, that's x squared minus 4x plus 16 with no remainder. And then if we take this x plus 4 and multiply it over, oh, this is what we get. We get f of x is equal to x plus 4 from here times x squared minus 4x plus 16. And this is the factorization of f of x. So what we realize at this stage is synthetic division now has two roles. One role is to find a number k that'll give you a remainder of 0, which will then detect what the factor should be. But it also gives you the quotient, which tells you the other part of the factorization. So it gets you both at the same time. And now a very natural question that comes up here is, well, how did I know to guess that negative 4? Because obviously I'm cheating. I made up the problem. So I know that negative 4 is going to work. And perhaps if you looked at this, you could say, oh, well, what if I plug in negative 4 for x? Since negative 4 cubed is negative 64, I should get 0. So maybe you can jump to here pretty quickly, recognizing that those are both cubes, and then realize that x plus 4 is a factor using this logic. But it's not always that simple, right? So in a few videos, we will spend a lot of time and effort discussing techniques for better guessing what k should be to make this work. It'll be fun. Thanks for listening. I'll see you guys next time.